at the bottom, standard deviation for your sample proportion. The formula goes, you take the square root of all of this stuff, p hat, that's your sample proportion, times quantity, 100 minus p hat, all divided by the number of pieces of data in your statistical study. That's what n is. Okay? So let's do an example. Let's apply this formula. Suppose we talk to 1,250 people, ask them whether or not they favor mandatory sentencing for drug-related crimes. Our sample proportion from our lovely poll was p hat is 25%. Find the standard deviation of the sampling distribution. All right. So all we do, plug straight in. And let's see, that. So sigma p hat is equal to giant square root of, okay, 25%, so we do 25 times 100 minus 25, all divided by, how many people do we have? 1,250. Okay? So you figure out the stuff on the inside of the radical first, 25 times 100 minus 25, divide that by 150. Take the square root of all of that. I got 1.22%. Okay, so remember, standard deviation tells us how far you are deviating from the mean overall. Okay, so according to our study, the majority of our results are going to be 1.22% away, left or right, from the mean. So, a word of advice when it comes to the exam, look for the key vocabulary words. Am I asking for standard deviation, or am I asking for standard deviation for your sample proportion? Okay, better watch out for those little extra bits. Okay? And as we talked about before exam 2, remember you always have to have what we call a margin of error. When you're doing a statistical study, you're working in an imperfect world. Things don't always turn out pretty. Things can go wrong. So we have to take into account this margin of error. In order to calculate this for a 95% confidence interval, you use the following formula. Okay. 1 over the square root of, that's how many pieces of data you're looking at, that's n, times 100%. That's your margin of error. Then to find the actual confidence interval itself, you take your sample proportion, subtract your margin of error to get the left bound, and then add the margin of error to your sample proportion to get the right bound. Remember, your interval goes from some value to another value, somewhere in here. All right, we've done this before. The same idea, we're just being a little bit more specific about the vocabulary. Okay, let's apply it. 1,200 people in a survey. We found that 47% plan to vote for Mr. Smith for governor. Okay, key thing to note here is 47% is close to 50%, right? There will be another case we're going to look at when you're evaluating of error. So 47 plus 2.887. I got 49.887. So our confidence interval goes from 44.113 to 49.887. What that tells us, we are 95% sure that the true proportion of people who plan to vote for Smith for governor is between, let's see, we need 44.113% of the voters and 49.887% of your voters. And this is overall. We're taking our sample data and we're applying it to the rest of the population. So up to 49.887 of the entire population is expected to vote for Smith. Can we be reasonably certain that Mr. Smith will lose the election? Yeah. Look at the numbers. He's got less than half of the votes, according to this poll. So yeah, we should expect to lose. Okay. Now, this is example 25. Notice our sample proportion is 47%. We're only 3 percentage places away from exactly half. Right? That's a nice one, right? When you're close to 50%, this is how to calculate it. But sometimes what you're studying, your sample proportion will be nowhere near 50%. If that's the case, we have another formula that we will get to after this exam question. I'll give you a second to write that down. So this works exactly like the example we just did. your sample proportion, and then you always add to get one end of your confidence interval, and you subtract to get the other. You add and subtract the margin of the error, okay, to get the confidence interval. And again, I apologize for my lovely note. For some reason, I'm missing a slide. So, there is a formula, okay, if you have a proportion not close to 50%, right? In one example we just did, we had a 47% same proportion, pretty close to 50%. If it's not, here's the missing one. I think it's in your slides, but for some reason, it's not in my lecture here. So not close to 50% to be used. P hat plus or minus 2 times the square root of p hat times 1 minus p hat all over n. It's not very clear on my slide, so I'm going to have to rewrite that. Okay. 2 formulas. You've got to pay attention to your sample proportion to tell you which formula to use. All right. Now, we're going to change gears a bit. We're going to get away from statistics, and we're actually going to start something called coding theory. Let's start by talking about something called modular arithmetic. Okay, hopefully we recall how to do old-fashioned long division, right? Take a number, divide it by another number. If it doesn't go into the number evenly, you get a remainder. You get 2 numbers left over. Okay, when we are working with modular arithmetic, the key thing to remember is we are talking about the remainder specifically. Okay. Here's an example. We count in sets of 10, right? 10 fingers, 10 toes. Our number system goes by tens. 10, 20, 30, 40, and so on and so forth. So if we take something like 53, and we divide it by 10, you get a remainder of 3. Right? Now, in modular arithmetic, we would say that 53 is equivalent to 3 in base 10, because we count in sets of 10. So that would be our base number. We're going to look at some examples. Now, here's the other thing to consider. There are lots of numbers that when you divide them by 10 will also give you a remainder of 3. If you divide 63 by 10, you'll still get a remainder of 3. Divide 73 by 10, you'll also get a remainder of 3. We say that all of these numbers that pop out the same remainder are congruent. It's a fancy way of saying that they are equal. You can't actually use the word equal because that means something else mathematically. So our new fun word is congruent. Division algorithm. Good old-fashioned division, right? We're just being a little bit fancy about how we're writing it out. So we have 2 numbers, n and m. I don't know why they like to use these 2 letters that are right next to each other when it's so hard to enunciate them. Okay. Say you have n and you're dividing it by m. Okay. Then you can do your whole division algorithm and you get your number on top of the house. You get a remainder. The division algorithm says that number on top of the house times this number that you divided by plus your remainder. That's what the Q, the M, and the R is. Take the number on top, multiply the number you divided by, by, add the remainder, you should get your original number. Okay. At the bottom, right here, take 38, and you want to divide it by 7. Okay. So if we write everything out, just so you can see where this comes from, you take 38 divided by 7. How many times does 7 go into 38? 5. All right, so you put 5 on top of the house. 5 times 7 gets us to 35. You subtract it, you get a remainder of 3, right? So if you look at what they wrote next, you can write 38 as 5 times 7, right? That's the number on top times the number you divided by. 35 times 7 gives you 35. Plus 3, so plus your remainder gives you your original number, 38, that we're talking about. The answer to a division problem is a quotient, so we'll denote that by the letter Q. We get a remainder, so we'll use the letter R. Try to keep it simple when we name our values. Don't worry, we got more. Okay. So, your turn. Find the quotient and remainder when n is divided by m. So we're doing 45 divided by 7. Okay. Okay. How many times does 7 go into 45? 6. 6 times 7 gives us 42. Subtract it, we got a remainder of 3. So that tells us Q, our quotient, is 6. Our remainder is 3. Now, if we want to be really fancy about it and rewrite our original number n, we can say 45 is equal to, right, talking about n, the number on top of the house, so there's our 6, times the number outside the house, 7, plus your remainder of 3. And, let's see if we follow the notation from the previous one. So n is equal to q times m plus the remainder. So our quotient was 6. The number we were divided by was 7. Our remainder was 3. Put a tail on that key so it doesn't look like a 9. Okay. Now remember, we're talking ultimately about modular arithmetic. And when working with modular arithmetic, the main thing we're looking at is the remainder when you divide by a particular number. Okay? So, congruence. Remember, we can't use the word equal because these numbers aren't truly equal. 53 is not the same as 63, even though with modular arithmetic, they both give you a remainder of 3. We say they're congruent. They're not exactly equal. So, in order to determine if two values are congruent, modulo whatever base we're talking about, all you do is check that their remainders are the same. Okay, so, for congruency, we use 3 lines instead of an equal sign, because remember, we're not exactly equal. And that fancy word modulo is just another way of saying whenever you divide by whatever base. So, for example A, is 36 congruent to 66 modulo 7? We are talking about base 7. Remember, we counted base 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So going to be, what, 9? Remainder 3. I'm being repetitive. We're talking about modular arithmetic. So I don't care about the 5 and the 9. All I care about are the remainders. This is remainder 3. That's remainder 3. So, yes, these are congruent. 38 is congruent to 66 mod 7. Only looking at the remainders. So for part B, what base are we in? 4. Base 4. Modulo 4. We're dividing everything by 4. Okay? So we write it out. 30 divided by 4 gives us 7 remainder 2. And 28 divided by 4 is equal to 7 remainder 0. Since the remainders are not equal, the two numbers are not congruent. Modulo 4. Okay. Mixing up the vocabulary there. The remainders themselves are not equal, so the original values are not congruent. Other examples of modular arithmetic that you actually use. 12-hour clocks. Alright? We're not in Europe, so we don't live on 24-hour time. We don't use that. Right? We use 12-hour clocks. So, this is base 12 counting. Once you get to 12, the numbers start over at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 started over, right? So, time here is measured in base 12. 29 hours after 2 o'clock, that's 2 plus 29 equals 31. 31 is the same as 7 mod 12. So 29 hours after 2 would be 7 o'clock. Congruence mod 2 in base 2. Any of you have done any computer coding or you know anything about computer coding? Binary code is mod 2. Modular arithmetic base 2. It's all zeros and ones. Two numbers. This also determines parity. In mathematics, this is a fancy word for saying is a number even or is it odd? All even numbers are divisible by 2. So, if you take a number and you divide it by 2, if you get a remainder of 0, that number is even. If you take an odd number, divide it by 2, you get a remainder of 1. So, there's parity. A number mod 2, if it is congruent to 0, is even. A number mod 2, if it's congruent to 1, it has to be odd. And then, like I said, positive integers in base 10, it's congruent to its last digit. So, go back to the example with 53 and 63. 53 divided by 10, remainder 3. You did 57 divided by 10, remainder 7. It's always the last number when you're working with base 10 or modulo. Now, like I said before, let's go back to our examples of 53 and 63 and 73. In base 10, okay, we're working in modular arithmetic. 53, 63, and 73 would all give us the same remainder, right? Each of those numbers would be congruent to 3 mod 10. We can't say they're equal because 53 is not the same as 63, is not the same as 73. Instead, we say these values are congruent. Since you have this group of numbers that are all congruent, we have something called a congruence class. It's a group of numbers that, in whatever base you're talking about, are all congruent. So if we're talking about base 10, 13, 20, because they all give you a remainder of 3. Okay? Two integers are in the same congruence class if they are congruent mod m. So if these values all give you the same remainder, they're in the same congruence class. The notation for this, we use a little bracket to say that this is the congruence class. Okay, the set of integers congruent to x mod m. So if we go back to our example, we would say that 53, 63, 73 are all part of the congruence class of 3, right? Because these are all equal to 3 mod n when we divide it by 10. There you go. For these numbers, -4, -1, 2, 5, and 8, those are all part of congruence class 2. Take a look. 5 divided by 3 gives you a remainder of 2. 8 divided by 3 also gives you a remainder of 2. So those are all numbers in congruence class 2. Now, a couple algebraic properties. Since it's arithmetic, you have to be able to do things like add and subtract and multiply. So, if we're talking about congruent classes, we have the following. If you have a congruence class of x, and you want to add to it the congruence class of y, well, you just put everything together, right? And you get the congruence class of x plus y. Same thing works for multiplication. Okay. Let's apply some of this. That 11 is supposed to be a subscript. It's supposed to be below z. So it's supposed to be z mod 11. That's another way to rewrite it. Find 37 plus 19, the congruence classes. Okay, well, according to our lovely formula in part A, you can take each of these and put it together. So that becomes the congruence class of 37 plus 19 on the inside. Add it up. Okay, 37 plus 19, I got 56. Right? But we're counting in base 11, so let's rewrite this. 56 divided by 11 gives us a remainder of 1. So 56 is part of congruence class 1 mod 11. So the remainder is what gives us our congruence class. Same thing works for part B. So we're looking at modular 3. Okay, that 3 is supposed to be a subscript. Find congruence class 4 times congruence class 5. Follow your formula up top, put them together. So this becomes 4 times 5. So we're looking at the congruence class of 20. But since we're in mod 3, we got to simplify that. All right. So 20 divided by 3 gives us 6 remainder 2. So the congruence class of 20 is equivalent to the congruence class of 2 modular 3. Right? We're dividing everything by 3. Right? That's modular arithmetic. We got a little bit more. Now, we're going to change gears a little bit more and get into some actual coding theory. Identification numbers. There is a method for how these are generated. They don't just randomly pick some numbers out of a computer. Okay? that one box of cereal. And it should have a self-checking mechanism for the number. We'll get into a little bit more detail about that later. Okay, most used types of error detection codes include an extra digit. At the very, very end, we call this a check digit. Okay. And different types of ID numbers use different ways of making up this check digit. Okay, different methods for calculating it. That's the next couple of things we'll see about. So, first one, FedEx. We use FedEx, UPS, so on and so forth. Okay. You know that random tracking number you get whenever you order something? Here's your confirmation number. You can track your package using the following tracking number. There's a way that that's calculated. Okay. It does stand for something. So, for FedEx, it's always a 10-digit number. The last number, 10th digit, is one check digit. That equals the remainder when the 9-digit number is divided by 7. All right. For that tracking number, 915, 754, 923, find the final check digit. Okay. So, there's the 9 numbers. We need to find the 10th, the last one. So we take the original and we have to divide it by 7. And then we need to find the remainder. Okay, so here's how you do this with your calculator. Because your calculator is not going to automatically tell you, oh, it's like 24 remainder 5. No, it's going to give you some ugly decimal. So you got to figure out what's going on there. So first things first. 915,754,923 divided by 7. 7 is our magic number when we're talking about the FedEx tracking. So punch that in. 915,754,923 divided by 7 gives me this ugly 130,822,131.9. What that means is 7 goes into 915,754,923 a lot of times evenly with some stuff left over. Okay? So that means you can take 7 times that monstrosity and get the number directly below your 915,754,923. So 7 times 130,822,131 gives me 915,754,917. Okay. So see, we're getting close to that original to find the remainder, right? The whole point is to find the remainder in this example. We take the number from step 1 minus the number from step 2. All right. 915,754,923 minus 915,754,917 gives me 6. So 6, since that's the remainder, is your check digit. So that's how you do it when you have some ugly number and you have a calculator, because it won't automatically tell you what the remainder is. You got to calculate the remainder yourself. Let's see. I think we can go ahead and set one more example.
How did you get the check digit?
Which one? You got to say it louder.
The check digit.
Check digit. Okay. The whole point of this example, shushing, stop fidgeting, people are asking questions. The whole point of this example, when we're calculating the check digit for Federal Express tracking numbers, you need the remainder when you divide the first 9 by 7. Okay? Well, so we take the first 9 numbers of our tracking code, and you divide it by 7. But if you do it on a calculator, it doesn't pop out remainder 6. It gives you this ugly decimal point 9, yada, 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 all this ugly stuff. Well, that tells you that all of the stuff before the decimal times 7, right, will give you a number directly below it. That's how many times 7 goes into it evenly before you get a remainder. That's why in step 2 we took 7 times all of that stuff before the decimal. And if you look at the two numbers, you are pretty close to your original 9-digit number, right? To find your remainder, all you do is subtract and zero. In this case, we got 6. So the remainder is 6, which means 6 is the 10th digit in that tracking number. Okay, here we go. Hang with me. Okay, I still got 3.5 minutes. A lot can happen in math in 3.5 minutes. Hang with me. So, UPC codes. We just talked about this. Right? UPC code for your box of cereal should not be the same UPC code for a slab of meat over in the butcher's section. Right? There is a way to calculate this. To find the check digit, that's the key thing, you have to add up all of the numbers in the odd position and multiply by 3. That's step 1. Then you have to take the sum of the numbers in the even positions. Then from there, you have to add a number that makes it a multiple of 10. So let's rewrite that last step. That number that you add is your check digit. All right, so went ahead and wrote out most of this for you. You actually set up, number it out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for your UPC code. Step 1, add the digits in the odd position and multiply by 3. You get 1 plus 1 plus 0 plus 0 plus 1 plus 7. Multiply all of that times 3. You should get 30. Try it for yourself later on. Remember, it's the odd positions. Step 2, take the values in the odd position. So 2, 4, 6, 8, 10. Right? Number each of your values. And I had 3 plus 0 plus 0 plus 0 plus 4 gave me 7. Okay. The third step, 30 plus 7 gives me 37. Remember, you have to add a number to that to make it a multiple of 10. Well, what's the closest multiple of 10 here? The next one up would be 40. So we have to add 3. So 3